Okay, so what we're going to be talking about today is graphing, ordering, and classifying real numbers, as well as identifying properties of real numbers. So, first thing I have here, and I love how the copy machine made this super light, so I'm going to help you by using all of my, look at this, colored markers to make this pretty again, okay? So here's what we're going to do. In the very middle of this, I have this set of whole numbers. And whole numbers are really like your counting numbers. They start with 1, and then 2, 3, 4, 5, and so on. All right, so those are the set of whole numbers. And you've known the whole numbers since you were in elementary school. So next, there is the set of natural numbers. Now, natural numbers include all the whole numbers, and they also include 0. So 0 is the one thing that's different that makes it the set of natural numbers. So now, we're going to get bigger from there. And so, we're going to go out to the set of what we call integers. So bear with me while I color this in. So integers are like the natural numbers, except not only positive, but negative as well. Okay? Now, we're going to expand out from there. And what I'm going to get to is the set of rational numbers. I guess I'm going to color code how this is all done. So I went back and I did the whole numbers. Let's underline that in green because the whole numbers are circled in green. And the natural numbers in blue. And then I had purple, which was the integers. So highlight that in purple. And then I did pink for rational numbers. Now, rational numbers, there's a whole categorization down here. These are, rational numbers are any number that you could write as a fraction. So now it also includes integers, because if you put a 1 under an integer, it becomes a fraction, right? Okay, and it's still the same number. So any number that can be written as a fraction is what we call a rational number. Now, I will also tell you, if you have a decimal and that decimal terminates or ends, then I can write it as a fraction. It is a rational number. If you have a decimal that repeats, remember repeating decimals? Repeating decimals can always be written as fractions. So all repeating decimals are also rational numbers. So you're going to find that, we'll put the little arrow down here, to the explanation of rational numbers. Now, there is a second set, and I'm going to do those in red over here on the side, because they are separate. They're not a set of a set of a set of a set. And these are irrational numbers. And irrational numbers are explained right here. So irrational numbers are numbers like the square root of 2, and pi. And in fact, any square root that you can't simplify is going to be irrational. Now, here's what makes it irrational. In decimal notation, the decimal never ends and it never repeats. That's what makes it irrational. So this class will be one of the first times that we're going to focus a lot on irrational numbers. They're going to come up over and over again. You cannot write these as a fraction. All right? So decimals that never end and never repeat. They are non-terminating. So let's go ahead and we're going to do a couple of examples. So if you go down here below, we've got a situation. Your school is sponsoring a charity race. Which sets of numbers describes the number of people P who participate in the race? So that number, P, what kind of number is it? Is it a rational or irrational number, do you think? It's rational. So out of the rational numbers, is it an integer, do you think? A number of people. It's pretty much got to be an integer. You can't have a half of a person or 3/5 of a person. So it's not going to be necessarily a fraction. It's going to be an integer. In fact, is it going to be a natural number? It's going to have to be, because it can't be negative. We don't have negative people. That's not a thing. You can have negative degrees, Fahrenheit, Celsius, but you can't have negative people. So when we answer this, we're going to say that this has to be rational. It's going to be an integer. And it's also going to be a natural number. Now, assuming that at least one person shows up for this race, wouldn't we also say it's going to have to be a whole number? Yes. Okay, so if each participant in the race made a donation of $15.50 to a local charity, which subset of real numbers best describes the amount of money that is raised? So first of all, is it rational or irrational? It's going to be rational, okay? Now, is it going to be an integer? Could be an integer. It could be an integer if two people, because 1550 plus 1550 are going to add up to $31. All right? So it could be an integer, but not necessarily, because it could end in 50 cents. Could be. Okay, so next thing we're going to do is graph numbers on the number line. So what is the graph of these particular numbers? Now I will tell you, the easiest way to sort this detail out is to convert everything into decimals so that you can see where they are on the number line, right? Because do you know where the square root of 2 is on the number line? I mean, do you know? No. Okay. So negative 5/2, do you know what that is? As a decimal, you should know that. You should be able to do this one in your head, right? Negative 5/2. Anybody? Negative 5/2. Come on. Someone's got to know. Ben. Negative 2.5. So this one right here, we've got negative 2.5. Now, we're going to want to do the square root of 2. So on your calculator, you're going to find the little square root key is right here, but you're going to need to use second. So second square root, put the 2 in there and click enter. And we find that it is about 1.4. Whoops, let's bring that down. 1.4. So that's about where it is. But here's the thing, that is an irrational number. That decimal never ends. So we're not going to write equals as in an equal sign. I'm going to write approximately equal, which is a squiggly equal sign.
Or 1.4.
Next, 2.6, what does this line mean? Means repeating. So this is going to be approximately equal to 2.6. So, or you could say 2.7. It doesn't really matter. But let's go ahead and do a number line. So we need to go all the way from negative 2.5 up to at least 2.6. So here's the way to go. We could go from negative 3 to 3. So let's make a number line. I'm going to put 0 in the middle. 1, 2, and 3. Negative 1, negative 2, and negative 3. And I'm going to go ahead and I'm going to plot these points. So negative 2.5 is halfway between negative 2 and negative 3. And right above this, I'm going to put negative 5/2. Because that's what I'm graphing right there. Now, square root of 2, we said was about 1.4, which is really close to halfway in between 1 and 2, but a little bit closer to 1. So I'm going to put that right there, put my dot, and I'm going to put square root of 2 above it, because that's where that's going to graph. And then I've got 2.6 repeating. Now technically, that's 2 2/3. So that's 2/3 of the way between 2 and 3. So maybe right about here. And I'm going to put 2.6 repeating, and I'm just going to plot it right there. So I have graphed those numbers on my number line. Needed a little calculator help to do it, but that's okay. Let's go ahead and turn the page. And I'm going to show you a little bit about how to do this without necessarily using a calculator. So let's go ahead, and we have ordering real numbers. And I have how do the square root of 17 and 3.8 compare using greater than or less than. So on one side, I'm going to have the square root of 17, and on the other side, 3.8. And I need to know whether greater than or less than goes there. Now, in order to figure this out, I'm going to use some common sense, right? Would you agree square root of 16 equals 4, right?
Yeah.
Would it make sense then that the square root of 17 is going to be greater than 4?
Yeah.
We don't know how much greater, but it's going to be greater than 4. So if this is greater than 4, is this sign less than or greater than? It's greater than. So there we go. All right? All right, so we've got 26 and 6.25 to compare. So let's try and do one. What's a square root that we know that's close to 26? 25. Okay, so square root of 25 equals 5. So we know that the square root of 26 is going to be greater than 5. Is that going to help us figure out which sign to put there?
Yes. Well, yeah.
How is that going to help us? Because this is greater than 5, but this is also greater than 5, right?
Yeah.
So let's try this. Square root of 36 is 6, right? So the square root of 26 is less than 6. That is definitively going to tell us what this is going to be. Because this is less than 6. This is greater than 6, so this is a less than sign. All right? So we're just using square roots we do know to help us make some predictions about square roots we don't know. Quick table for you here is our properties of real numbers. When you do your homework today, you're going to be looking at some equations, and you're going to have to figure out which property is being demonstrated between the left hand and the right hand side. So I'm going to go right here to commutative. And when I go to commutative, you can see that I have a property for addition and a property for multiplication. In fact, it looks like I have a lot of addition property and multiplication properties. But I don't seem to have any for subtraction or division, do I? That is true. These properties are just for addition and multiplication. So my commutative property tells me that I can change the order in which I add or multiply without changing the answer. So I'm going to put right here, this is about changing order. So that means that A plus B is going to give me the same answer as B plus A. And A times B gives me the same answer as B times A. Now, associative is different. This has to do with grouping. So I can group differently and still get the same answer. This has to do with grouping. So notice, would you agree, on the left-hand side and the right-hand side, my order is the same, A, B, C, right? But on the left-hand side, A and B are in parentheses, whereas on the right-hand side, B and C are in parentheses. We can do that we'll still get the same answer. Same thing with multiplication. I have on both sides A, then B, then C. On this side, A and B are in parentheses. On this side, B and C are in parentheses. Still going to get the same answer. Now, the identity property, I like to think of this as the itself property. What can I do to a number and the answer is itself? So I can add 0 to a number and I still get that same number. That's the additive property of the identity property of addition. This is the identity property of multiplication. I can take a number and multiply it by 1 and I still get that same answer. All right? The inverse property is asking me, what can I do to a number to undo what I've done? So this undoes something. So if I have a number, I can add its opposite, and I will get 0. I have undone that number by adding its opposite. And with multiplication, I can take a number, multiply it by its reciprocal. When I do that, I get 1. All right? And lastly, you know this one, we've been doing this for years, the distributive property. The distributive property is not a property of addition or multiplication. It is actually a property of multiplication with respect to addition. This is multiplying. This is the adding right there. So what we're going to do is multiply this times this, add it to this times this. And you've done that before. So what I want to do is go down to the bottom of the page, and I want to have you tell me what property do you think is demonstrated in this example? What property do you think this looks like?
Inverse.
This is inverse. Inverse. Inverse of multiplication, because this is a number times its reciprocal gives you 1. What about this? Example B. It is commutative. All right? What is grouped has not changed. The 3 and the 4 are grouped together on both sides. What has changed is the order of the 3 and the 4 in the group. So this is actually the commutative property of multiplication. Okay, what about C?
Associative.
This is actually distributive. What I've done is multiply the 3 times the G and the 3 times the H. So this is distributive. Now, one of the things you're going to do on your homework, and this can be somewhat challenging, but it really helps you learn what you can and cannot do with algebra. And that is, we are going to take this, and we are going to prove that this is 3. Now, I know when you take a look at this, you can probably see that it is. But can you prove that it is using just your properties? So the first thing I'm going to do when I do this is I'm going to use my commutative property. All right? So this is going to equal A. I'm going to leave my brackets here, and I'm going to put negative A plus 3. So all I did was use my commutative property. So commutative property of addition. All right? What I'm going to do next is I'm going to use my associative property of addition. So I'm going to group the A and the negative A. So I have A plus negative A plus 3. And this is associative, don't just do ASS period, that bothers me, do ASSOC of addition. All right? Now what I'm going to do is, you know that A plus a negative A, any number plus its opposite, equals 0, right? Okay. So this equals 0 plus 3. And that is the inverse of addition. Lastly, what tells me that 0 plus 3 equals 3? Identity property of addition.